Welcome back to the Deep Dive. Today we are diving deep into one of the most frustrating and, frankly, expensive problems in AI today, alignment.
Mm.
We're talking about how you take a massive large language model, an LLM, and get it to produce text that isn't just coherent, but is, genuinely helpful, harmless, tailored to what a person actually wants.
And that helpful and harmless part, that's where the massive costs are hiding right now.
Yeah.
I mean, you look at the standard methods.
Like RLHF.
Right, reinforcement learning with human feedback, or even DPO, direct preference optimization. They're incredibly powerful, don't get me wrong, but they require this costly, really resource-intensive retraining of the model's billions of parameters.
Every single time preferences change.
Every single time. Or for every new task. It's basically a computational black hole.
And that expense, the sheer scale of it is why there's this frantic search for what people are calling test time alignment. The idea is, it's simple, but it feels kind of revolutionary. You keep the big foundational model completely frozen, no changes, and instead you align the output as it's being generated.
On the fly. And the research we've pulled apart for you today is a huge step toward that goal. It's a paper introducing something called Textual Model Predictive Control, or TMPC.
TMPC.
Yeah. And our mission today is really to understand how TMPC reframes text generation.
Mm-hmm.
It stops thinking about just predicting the next word and starts treating the whole process as a formal sequential decision-making problem.
By doing that.
They manage to get these huge quality gains without ever touching the model's weights.
Okay, let's unpack this, because treating text generation as a decision-making process, that feels like the key conceptual shift here. The paper uses the Markov Decision Process Framework for this, the MDP.
Mm-hmm.
So when you look at it through that lens, what were the sort of fundamental weaknesses they found in all the existing test time methods?
That MDP framing, where every choice, every token is an action that leads to a new state, it immediately exposes the limitations. It forces existing methods to choose an action level. And that choice, well, it traps them between two fundamental conflicting problems.
The researchers have a great name for them.
They do. The two curses.
So a structural conflict. Let's start with the first one. The curse of horizon. What is that?
The curse of horizon hits methods that try to make their alignment actions at the finest possible level, the token level.
So word by word.
Word by word, or even smaller. These are the guided decoding methods, things like ARGS or RAIN. That is to just nudge the model's choice for the next single word, to push the output in the right direction.
But the final output could be a 1,000-word article or a whole block of code.
Precisely. If your whole generation trajectory is thousands of steps long, that's your horizon. Trying to judge the quality of the final output based on a choice you made at token number 5, it becomes computationally unreliable.
The signal gets lost.
Completely. It's like trying to judge the stability of a skyscraper based on where you placed a single brick on the first floor. The credit assignment was that early choice, good or bad, it becomes brittle, fragile, and the error just accumulates.
That makes perfect sense. Constant, tiny adjustments over a huge distance, you're bound to drift. So if we can't align token by token, what happens if we go to the other extreme?
That's where you hit the curse of dimensionality. This one affects methods that define their action at the complete opposite end, the entire response level.
Okay.
The best example is iterative refinement, like test time preference optimization, or TPO. You generate a full long response, you get feedback on the whole thing, and then you tell the model, okay, rewrite this entire thing to make it better.
So now the problem isn't the long journey, it's the sheer size of that rewrite command.
Exactly right. You're rewriting a whole long form answer, the number of possible ways you could change it. The action space is astronomical.
A needle in a haystack.
A needle in a universe of haystacks. It's computationally intractable. So the search for a better version becomes unstable and erratic. You basically trade the fragility of long-term planning for the intractability of a giant action space.
It's a perfect catch-22. You're either too fragile or too complex. And here's where it gets really interesting, because this framing is what forces us to look for a dynamic middle ground. How does TMPC solve this?
TMPC borrows its core idea from control theory, specifically Model Predictive Control, or MPC.
Which is used in things like robotics,
Yeah.
right? Manufacturing.
Exactly. Standard MPC is great at these kinds of sequential problems, but it depends on something that text generation just doesn't have: predefined hard boundaries between steps.
Right, like in a factory, you know exactly when one step ends and the next begins. Text is just fluid.
It's totally fluid.
Good.
And TMPC is so novel because it figures out how to impose those boundaries dynamically, on the fly. It does it with two key principles. This is really the aha moment in understanding how it escapes those two curses.
Okay, lay out the first principle for us.
The first one is called hindsight, sub-goal identification.
Hindsight, so looking backward.
Exactly. It flips traditional planning on its head. Instead of trying to guess what a good next step should be, it generates a few initial drafts and then analyzes them retrospectively. It looks backward to find the meaningful little chunks, the intermediate outputs that actually resulted in a high reward score.
So it writes a few messy drafts, and then it goes back and highlights the 2 or 3 sentences that were actually perfect. It's finding success after the fact.
That's the mechanism. And those high reward chunks, they become your sub-goals. For machine translation, a sub-goal might be one perfectly translated sentence. For coding, it could be one function that works correctly. By finding these validated pieces, TMPC dynamically shortens the planning horizon.
It breaks the huge problem down into a series of smaller, manageable, proven wins.
Which avoids the first curse.
Okay, but how do we avoid the second one, the curse of dimensionality, where rewriting the whole thing is just too big? That must be the second principle.
Correct. It's called sub-goal condition regeneration. Once TMPC finds those high-quality sub-goals, it doesn't just forget them. It stores them in a memory buffer.
Okay.
Then, for the next planning step, the model is explicitly conditioned on that buffer. The instruction is basically, generate a new response, but you must include and build upon these successful pieces we've already found.
Wow, that sounds incredibly stabilizing. So you're not doing a brute force search anymore. You're locking in your wins and just focusing the search on the parts you haven't figured out yet.
That's exactly it. It guarantees stable, cumulative progress. You're not starting from scratch every time, which completely sidesteps the error accumulation problem. And because you're conditioning the generation, the search space for the new part is drastically smaller.
And the crucial part for you, the listener, is that TMPC does all this with a frozen LLM. It's just using the base model as a proposal engine. No expensive fine-tuning.
None at all.
That's a huge claim. So to prove this wasn't just a one-trick pony, they tested it across 3 really different tasks. Let's start with the one that had the clearest boundaries. Paragraph-level machine translation.
Right. They used a strong model, Almeida-DAF 3.18b Instruct, on a tough literary translation benchmark. They tested a few language pairs, including Chinese to English, which is notoriously difficult.
And the results?
They were stunning. TMPC was either the best or second best across all the language pairs. It massively beat strong baselines like best of 60 sampling.
Where you have to generate 60 different full translations just to pick one.
Yeah, a very brute force method. And for Chinese to English, TMPC's quality score actually exceeded the performance of GPT-4o.
All on a frozen 8 billion parameter model with the smart planning layered on top, beat one of the biggest proprietary models out there.
On that key quality metric, yes, it really shows the power of smart planning over just raw model size.
And there was another metric that really stood out to me, the null alignment ratio.
Ah, yes, the NA ratio. This measures how often a sentence in the original text fails to get correctly paired with a sentence in the translation.
What was TMPC's score?
For Chinese to English, it was 0.00%.
0. So perfect sentence pairing. For you listening, that means it didn't just produce a high-quality translation, it perfectly kept the structure of the original document. No missed sentences, no jumbled paragraphs. That's incredible consistency.
Now for the tougher test, long-form response generation. Here you don't have those natural sentence boundaries, so how you segment the text is critical. They use the HHRLHF dataset.
And this one is really about efficiency, right? Pitting smart planning against just raw sampling.
Exactly. TMPC only generated 10 total responses in its process. Just 10. And yet, when judged by GPT-4, its outputs consistently beat the best of 20 sampling method.
Which generated twice as many outputs.
Twice as many. It's the definition of efficiency. Better results with less work through smarter strategy.
And the raw reward scores back that up too. TMPC got an average reward of 4.60, which was way higher than DPO, a powerful training time method, which only got 3.95.
Right. And again, DPO requires that expensive retraining. TMPC, with a frozen model, found a better path to alignment. It's because it's systematically climbing the reward landscape by confirming good parts, not just averaging out preferences like DPO does.
Okay, the third test seems like the hardest. Program synthesis. Coding. The reward here is binary. The code either works or it doesn't.
Yep, using the MBPP dataset, and this is where that cursive dimensionality is usually a killer. One missing semicolon, one indentation error, and the whole thing fails.
We saw that with the baselines. Best of 35 sampling only got a 50% pass rate.
And TPO was just behind at 48%. If the model keeps making the same kind of error, more sampling often doesn't help.
But TMPC...
TMPC achieved a 61% pass rate, a huge jump. And you can see exactly why. If an early attempt generates a piece of code that passes 2 out of 5 tests, that piece gets locked in the buffer as a validated subgoal. The next attempt then focuses on solving the other 3 tests, building on that proven foundation.
It's not reinventing the wheel every time, it's systematically building a working solution. But all this planning, I mean, it sounds complex. Is it too slow for the real world?
That's another major win. It's surprisingly efficient. A full, long-form response with all the planning steps took about 108 seconds.
Which is an instant,
But compared to those token-level methods that suffer from the curse of horizon, RAIN took over 1,900 seconds for the same task. ARGS was over 360.
So TMPC hits this amazing sweet spot. Better results than expensive training methods and better results than other inference time methods, all while being practically fast.
And it's robust. The researchers found that even if they used a weaker reward model or fed it noisy feedback, TMPC's performance stayed stable. That buffer acts as a filter. It only keeps the good stuff, so low-quality ideas don't derail the whole process.
So if we pull back and look at the whole picture, TMPC really is this elegant solution to a deep structural problem in LLM alignment.
It is. It unifies that sequential decision-making view, and it resolves that fundamental conflict between the curse of horizon and the curse of dimensionality. It does it by looking backward to find what works and then planning forward based on those proven successes.
So what does this all mean for you, the person who actually relies on these models? It means the next generation of LLMs, especially the smaller ones, might not be trapped in that endless, expensive cycle of retraining. We're getting tools that let us steer and correct model behavior on the fly. That means faster deployment of better, more trustworthy AI without the astronomical compute bill.
It's transformative efficiency. But we have to touch on the core limitation they mention in the paper. TMPC is a steering mechanism. It can only generate outputs that the base LLM is already capable of producing. It can't create new knowledge.
It can't teach the model something it doesn't know.
Exactly. And this raises a really important question for you to think about as this tech moves forward. If a language model is fundamentally limited to what it's already been trained on, how far can we really push these test time alignment methods like TMPC before the only way to get better is to go back to that painful, expensive process of massive retraining? That divide between steering what's there and teaching something new, that remains the ultimate frontier.